Hi, welcome to this video on solubility equilibrium. So in this video, we're going to talk about a little bit of background about solubility and how it applies to equilibrium. And then we'll do a few easier calculations using some rice table setups to just discuss equilibrium expressions and how we can find what the equilibrium values mean and how we can find concentrations of specific substances. So starting off, we have the concept of the solubility product constant, which is KSP. This is an equilibrium expression or an equilibrium quantity, so we put in SP for solubility product. So you probably remember from previous that solubility, when we use that term, is referring to the amount of solubility that something has or how much it dissolves. So when we talk about solubility product, right, typically the products of our solubilities are ions. So it's basically looking at how many ions are present in our solution when something dissolves. So this leads us to a little bit of a lie that we've told you. So we tell you all these solubility rules and we say that things are insoluble. Well, that's not really the case. There's actually many different degrees of solubility. When we say something is soluble, we're basically saying more than 3 grams will dissolve in 100 milliliters of water. That's really where they make the cutoff. So if we can get more than 3 grams to dissolve in 100 milliliters of water, we would say that's soluble. Now, we have some solubility rules that we say are always soluble, right? That means more than 3 grams are going to dissolve in 100 milliliters of water. When we say something is insoluble, it's just not going to have as much dissolved, but it doesn't mean that it won't. So every substance has a set degree of solubility. Some are just really small, so we tend to classify them more easily as insoluble. Well, in this chapter, we're going to be a little more specific. So if you can actually see that a salt is insoluble, which means that you would see that solid stuff, right, settling on the bottom, that actually is indication that it's saturated. So hopefully you remember that from first year chem, because saturation means that you have reached the maximum amount of solubility or water molecules that are capable of breaking apart those ions. And so there's no more water molecules available to break those ions apart. That usually has to do with the strength of the ionic bond and things like that. So solubility does tell us a little bit about the strength of the bond. Saturated solutions, right, of salts, when we refer to something as saturated, are going to be present due to a chemical reaction taking place, are also another type of equilibrium. So we're going to talk about two different. We're going to talk about just having a solution and its solubility and reaching that saturation point, which we would consider equilibrium. And then we're also going to talk about chemical reactions that can take place with saturated solutions and that side of it. So we'll talk about chemical reactions a little bit as well. All right, so slightly soluble salts are always going to establish what we call a dynamic equilibrium. And that's basically just means that we put a salt into our water and the water molecules are going to break it apart until it reaches equilibrium, meaning the rate of dissolving is equal to the rate of precipitation, meaning the reverse reaction, or it's staying as a solid. So it will reach its maximum saturation point. At this point, that is when we would say it is an equilibrium. So for example, AgCl, we've got an example over here, is a solution of silver nitrate. And so they're taking this over here, they're taking this colorless silver nitrate and they're adding it to a solution of sodium chloride that's also colorless. And when that happens, we see, oh, look at this nice white precipitate. That white precipitate is the silver chloride solid. And so then we know that the sodium nitrate is spectators. Those are still floating around. They didn't really do anything. So when the solutes were first added to water, there are not any ions initially present. Okay, that's really important. And then as the solution proceeds, your concentration of ions is going to go up right? So I might have more ions until equilibrium is established. This is really, really important. When we reach equilibrium, that is saturated. This is really important because in the AP exam, they like to use the word saturated instead of equilibrium when they're talking about solubility problems. And they kind of like try to trick you with that because they use that saturated vocabulary, and really that means they're at equilibrium or they've established equilibrium at that point. The equilibrium constant is no more than the product of the ions in the solution because we ignore solids. So it doesn't matter how much of the solid I put in there, right? What matters is the amount of ions that are floating around. That's what our equilibrium is calculated based on. All right, so looking at that reaction, one thing that's really important is we typically, for saturated solutions of anything, when we're talking about solubility, we're usually going to use the net ionic equation. So yeah, I could go in there and write the entire equation. Oops, let me change my thing. I could go in there and write the equation for everything, and I could say, okay, AgNO3, right, plus NaCl. This would take forever. It's going to make in those two solutions, and then I double replacement, AgCl, and then I make NaNO3. But do we really care about the sodium or the nitrate? No, we really don't. The sodium and the nitrate are spectators. So when we write an equilibrium solubility equation, we're going to write a net ionic equation. We're really talking about the ions that are reacting. So the saturation or the solubility equation is always actually starting with whatever solid you have in there. Don't ask me why I crossed off the chlorine. Just ignore that. Pretend I didn't do that. Actually, just to make my life easier, I'm going to remove that so that you don't get confused later. Okay, so as we're working through, we always are talking about, for a saturated solution, putting the solid in there. So I'm going to put the solid AgCl precipitate in my solution, right? So we make a precipitate, but a little bit of that solid is actually going to dissolve. So that silver chloride is going to be added to water, and really the water just becomes surroundings, and it will eventually equal saturation, right, which is equilibrium, and that's going to be a single Ag ion that's aqueous and a single chlorine ion that's aqueous, right? So notice I put my ion charges on there. That's really important. So that's essentially your equilibrium equation, chemical equation. We're going to use the net ionic. We don't care about any of the other stuff that's going on. This is essentially what we're paying attention to. The solubility product expression for the AgCl precipitate is really easy to do because you would write KSP, right? Well, normally it's concentration of your products over your reactants, but we're not going to include the AgCl because it's a solid. So really, it just becomes my ions, which is Ag plus to the first, right? And Cl minus to the first as well. The AgCl does not appear in the equilibrium expression because solids are going to be left out. So we talked about that in general equilibrium. Solids are going to be left out because their concentrations, right, do not change appreciably. And that's the same for solids and liquids, I guess, would be a better way to say, like water, right? Their concentrations or quantities change very little. So since they don't change much, we don't really include them. Very little. So there's not a whole lot of change going on there. So there's no point in including them in the equilibrium expression because overall it's just going to pretty much be the same. All right. So what I want you to do in this case is I want you to just practice writing the equilibrium expressions for each of the following. And then you can find its value in the table. It's supposed to be on the next page, not above. But your KSP, right, is going to be based on your ions. So my first one, for example, would be Ca plus 2 brackets. Notice I'm using the brackets. The reason I'm using brackets is because these are all ions. Ions only exist in solutions, so therefore they have concentrations. And it would be F minus, and because that is a coefficient of 2, that's 2 to the power of 2. All right, I want you to go back through and do these other ones, okay? So take a second, write the KSP expressions for those. They should be very easy. Make sure you include your ion charges on each one. All right, in this table of equilibrium or solubility equilibrium constants, right, this gives you a lot of really good information. So you're going to be given KSPs if needed, or you'll be given information to calculate a KSP. We'll talk about how to do that later. But one of the things you want to pay really close attention to when you're doing when you're looking at these KSP values is what do they mean? And so that comes down to here with this little concept. So when we're estimating a salt solubility from its KSP, right, our KSPs are basically just the products, which are, in this case, your number of ions, right? So number of ions. That's really all that is, okay? So if those are your products or your just total number of ions, right, then the more ions you have or the higher the KSP, then the more soluble your substance is. So relative solubilities, so keep in mind we say relative, that means we can compare solubilities of two different substances if we compare their KSPs, right? So if I compare the KSP of, I'm just going to pick two, let's say silver iodide, right, that has a solubility of 8.3 times 10 to the negative 17. That's really small compared to strontium sulfate, that is a solubility of 2.5 times 10 to the negative 7. Assuming I picked those two because it's the even number of ions, right? 2 ions and 2 ions. When I look at those two, assuming I have equal numbers of ions, so if those would split, they each split into 2 ions, I can pretty much assume strontium sulfate is more soluble than silver iodide because of this KSP value. That's really, really small, which means it doesn't have a lot of ions in solution, hence not very soluble. 10 to the negative 7 is bigger, so therefore it has more ions or more product in solution, so it must be more soluble. So really easy to come up with those relative solubilities, so you can compare what's more soluble or less based on their KSPs, okay? But keep in mind, when you do that, you want to do it with the same ion-to-ion ratio, because if we don't pay attention to the ion-ion ratio, right, the solubility is based on the number of ions present. So something that breaks into more ions, obviously, is going to have a much greater overall KSP value, even though it might be equal or less soluble than something else. Please don't forget also that solubilities can change with temperature. So some substances are less soluble in cold water while others are more soluble. So there are several things that you just got to be careful about. So a general rule of thumb is most things become more soluble at higher temperatures for ionic salts. However, some ionic salts become less soluble, and so it doesn't happen a lot, but it's kind of like in first year when we talked about gases being less soluble. There are some ionic compounds that are less soluble at high temperatures. So it doesn't really fit with what we normally think, but that's kind of what it is. All right. So we can use our table if we know those, and these are for you for reference as we work through problems through the chapter or whatever if it's not given to you. All right. Okay, so let's getting into determining our KSP from experimental measurements. All right. When we have, I can't get this to go straight, I'm sorry. It's all jacked up. Okay, when we are given experimental measurements, right, KSP values have been given to us to use because scientists have found those using careful laboratory measurements with a lot of different methods and whatever. So we can use a KSP that's been provided to us with relative certainty that it's going to be pretty accurate. Now, you may look from online resource to resource, and you may find them be slightly different, but they're not going to be that far off. Okay, so example 2. Lead 2 chloride is going to dissolve to a slight extent in water, right? So it's something that we typically know, like halides, remember the halogens are typically pretty soluble except for when they're silver, mercury, or lead. Well, now we know that lead is going to be a little soluble, but not a lot. So first thing we want to do is write the equation, right? The dissolving equation. So dissolving equation, super easy. We're going to take our lead chloride. It would actually help if I picked the pen. Sorry about that. So I'm going to take PbCl2. And you can add the water, but keep in mind this is a solid. We're going to add it to water. I usually like to show the water. It doesn't really matter. You don't have to. You can omit it. Sometimes I show it, sometimes I don't. But this is going to end up reaching equilibrium. When it does so, I'm going to have lead plus 2 ions and 2 Cl minus ions, right? So we want to pay attention to our stoich there. All right, so there's our equation. Those are both going to be aqueous. You don't really have to write this as long as you understand it and know it. It's not something that's going to be a big deal. But remember, those ions are aqueous, floating around in the water and all that. It broke them apart. So then it says, calculate the KSP if the lead ion concentration has been found to be 1.62 times 10 to the negative 2 molar. Okay, so this is where I really like to use the rice tables because I think it's important for you to get used to these and to see them more often as rice tables. So rice, obviously the R is the I, right, is the reaction. The I, the C, and the E. Okay. I is your initial. Well, typically, if I have lead chloride and I put that into, right, I take the lead chloride and I add that solid to water, right? So initially, I'm going to do solid plus water. That's what I have initially. I don't really care about the concentration of my solid because it's not going to be part of my equilibrium expression, right? But usually, we start with 0 of each of our reactants, okay? So I have no lead, I have no chlorine ions initially. Well, what's going to happen here? I don't really care what happens to my lead chloride. I mean, obviously, realistically, we would know that that's going to subtract, right? Obviously, we're going to lose some quantity of it. Over here on my product side, though, what I'm going to see happen is I'm going to see that my lead ions are going to increase by some quantity of X, and my chlorine is going to increase by some quantity of 2 times X, right? So we can easily see that. So at equilibrium, I should have X amount of lead ions and 2X amount of chlorine ions, right? So then it becomes an easy solve problem. So we're always going to be increasing our amount of ions for our solubility, unless we were already at equilibrium and we were disrupting it. But typically, when we're making the solution and it's not talking about anything else being present or the system already being at equilibrium, we're basically saying we're starting with no ions, we're putting the solid in there and dissolving it. So your ions are always going to be positive. All right, so pretty easy once we do this, right? So then one of the things that it says calculate the KSP if the lead ion concentration is found to be 1.62 times 10 to the negative 2. Well, that tells me that that's X, right? Because that's what my lead concentration is. So if my concentration of lead, right, is 1.62, then my concentration of chlorine is 2 times that, right? Is 2 times 1.62 times 10 to the negative 2 molar. So overall, my chlorine concentration is going to be 3.24 times 10 to the negative 2 molar at equilibrium, right? So now I have my concentrations of both things at equilibrium. I can do a quick, easy calculation to find the KSP because that's really what I wanted, right? So my KSP expression, we've already talked about previously, but KSP is, in this case, concentration of lead plus 2 with brackets times concentration of Cl minus, and keep in mind that's squared, right? So then all we have to do is plug in. So once we have these equilibrium quantities, we're just plugging in. So KSP is going to equal, and so in this case, we're going to have 1.62 times 10 to the negative 2 molar. And then we're going to multiply that by 3.24 times 10 to the negative 2 molar, and we're going to square that because that's important. All right, so there we go. So easy calculation, plug that into your calculator, and your KSP is going to be 1.70 times 10 to the negative 5, and we don't have to worry about using any kind of units on our Ks. All right, so pretty easy calculation. The rice table, while not required, I like it because I think it helps make it a little more obvious of like, okay, here's what I have. This is what I have at equilibrium. Okay, so I have the lead amount. My chlorine should be double, because I see a lot of students miss that stoichiometry part of it. I think the rice table helps solidify that and make it a little easier. So I'm going to tend to use that more often when I'm showing you your calculations, even though I know you could probably reason it out without. I just want you to be able to see it, have an idea of what's going on. Okay, so let's try another question. So in this next question, we're calculating KSP again from solubility 1. So it says copper 1 bromide has a measured solubility. So when it says its solubility is something, what it's telling you is it's telling you what X is. So whenever it says the solubility or the molar solubility, that's X. That means that's how much it dissolves, right? So that's how much it loses, or because solubility is the amount that dissolves, right? And so that is how much is dissolving, or what X is, okay? So keep that in mind. That's that change that's happening. So we're going to do copper 1 bromide. So I'm going to have copper 1 bromide, which is going to be CuBr, solid, right? And we're going to add that to water, because I like to put the water, but you don't have to. And when we do that, it's going to end up in equilibrium with copper plus 1, and nicely bromine minus 1. Those are 1 and 1, so the stoichin's going to end up being really nice. So for my rice table, I'm going to set that up. All right. Again, I don't really care about my solids because it's not going to be part of my equilibrium expression. We know that's going to lose some amount, right? The X. But we're going to assume we start with 0 of the bromines because it's not specifying anything else. We're going to see plus X of copper plus X of bromine because it's a 1-to-1 stoic ratio. So at equilibrium, I should have X copper and I should have X bromine. Well, what we know is that that X, right, we talked about a minute ago, that X is what these concentrations are. So at equilibrium, this is 2.0 times 10 to the negative 4th molarity. And this is 2.0 times 10 to the negative 4th molarity, because this equals X, right? And there's nothing else attached to it. So then all I'm going to do is set up my KSP expression. You always want to write your KSP expression because it's usually a point in your AP stuff, in your AP for your responses. So we'll have copper plus 1. Make sure you've got charges. Bromine minus 1 or minus. Okay, so always make sure you got those, because if you don't put those, then you're going to lose points. The other thing is it helps keep you from making a mistake on accident. So KSP equals, and really we're just going to take 2.0, times 10 to the, what is that, negative 4. And that's my molarity. And we're really just going to square that, right? Because I'm going to do it twice. You could also show that it was twice, but anything times itself is squared. So then when I calculate that put that in my calculator, my KSP is going to be 4.0 times 10 to the negative 8. All right. Pretty easy KSP. All right. So hopefully we all got that. There we go. Okay, so on this next problem, let me move this up. I'm going to give you the answers to this one, and I want you to try it on your own. Now, I just do want you to pay really close attention to the KSP, or not the KSP value, that the bismuth sulfide is 2 bismuths and 3 sulfurs. So that's going to affect your X, and it's going to affect your KSP expression. So when you solve for this one, what you're looking for is, hopefully you get, if you do your math correctly, so set it up with your rice table, plug it into your KSP expression, you should get 1.1 times 10 to the negative 73. Yes, negative 73. Super duper tiny. That tells you the solubility of this is like almost non-existent at this point. All right? So I want you to try this one on your own. Make sure that you have that one completed and when you submit your notes to me, because I'm going to be checking that. All right. Another example is the other way. So we could be given a KSP, and when we're given a KSP, we can be asked to solve for the solubility of the calcium carbonate in pure water. So we can basically be asked, like, what is that solubility in moles per liter, or we can ask grams per liter. So we're going to work both. All right, so we're just going to practice, do both. It's not too hard. Pretty easy question. All right, so first thing we always want to start with, just to make our lives a little easier, is the reaction. So we've got CaCO3, solid, right, plus my water. And I'm going to put that in there. It's going to end up in equilibrium. And I'm going to have calcium plus 2 ions. And I'm going to have carbonate ions. Now, this one's nice because everything's 1 to 1, so that keeps my numbers a little nice, right? That last problem was a little bit of a doozy. All right, so we've got R for reaction, I for initial amount, change, and equilibrium amount, right? As always, we don't really care about our solid, right? The solid won't matter to us. We're not really paying attention to the quantity because the amount of it isn't going to change drastically. Okay. The other thing we're going to look at is our initial amounts, right? So based on this, we want to calculate the solubility. So we're going to assume, just like anything, we didn't have anything of those to begin with. And our change is going to be plus X for both of them because it's nice, right? So then at equilibrium, they're both going to be X. What we don't know is what X is. Nicely, though, is we have a nice KSP expression. My KSP is calcium ions, right? In brackets, times carbonate ions. All right, well, what do we have? We have the ability to solve because we have the KSP. So it gave us KSP this time. So we're going to plug in, and we're going to come over here, and it tells us what the KSP is. -9. That's not super soluble, but it is a little bit soluble. So we're going to plug in 3.8 times 10 to the -9 is going to equal X squared, right? Because it's X times X. So then easy math, right? We're going to square root both sides. And so my X is going to end up being, when I put that in the calculator, and I have 2 sig figs, I'm going to get 6.2 times 10 to the -5. And that's going to be molarity or molar, right? And so that answers actually question A because this is moles per liter. So that's the same as saying 6.2 times 10 to the -5 moles per liter. Correct? Okay, so super easy. I've answered the question for part A. Part B, I'm going to do over here on the left, which is a little out of the way, but I just ran out of room, is asking me to find it in grams per liter. Well, I mean, I already have moles per liter, so really I'm just taking moles and going to grams, right? So that means I just need molar mass. So we're going to take 6.2 times 10 to the -5. Now keep in mind, this is really just taking molarity and converting it to density, right? Per 1 liter. And then you're just going to do quick molar mass, right? So for every 1 mole of, and this is going to be of the calcium carbonate, right? I would add up my molar mass. So I'm going to like add up calcium 40.08 and 12.01 and 48, and I get 100.09 grams of calcium carbonate. So when I multiply that, right, essentially it's multiplying it by like 100. So it ends up being 6.2 times 10 to the negative, let's see, 3 grams per liter. So this would be my density instead of my molarity. So super easy. We could also have used the dirt over the P, whatever. But that works better for gases. Okay, so hopefully not too bad. We have questions on here. But really it's the same. You're just with what you're given, what you have. If you set up your rice table, you can easily see what you're using or what you're doing. So as soon as I found X, I knew X was the solubility. So that was super easy. So when it says calculate the solubility, I knew I was calculating X because that's what solubility is of the calcium carbonate. All right. Here is another problem that is very similar to that same one. So I want you to do this one again on your own. So that way you can get practice and become super good at these. So I'm going to give you the answer so that you can check your answers on that. So when you calculate, you're just calculating the solubility, which really means you just want moles per liter, right? So I'm not going to ask you to do grams per liter all the time, but sometimes on the AP exam, they like to integrate those things, and so they'll throw that in there or whatever. So your actual answer for your molar solubility on this problem, when you solve for it, is going to be, let's see, 3.3 times 10 to the negative third molarity. Okay, so on this one, that is going to be your solubility of the copper iodate. And so when you're finding this one, you're going to do it the exact same way we just did the other one. The only thing that's really going to be different is you're going to have 2 iodates. So it's going to be 2x. That's going to make your math a little bit harder, but not bad. So you should be able to do it and try it, and we'll talk about it if you have questions in class. Okay? All right, make sure you complete both of those practices before you submit your notes, and come see me if you have questions or ask them in class.